Okay, assalamu alaikum. Today we are going to start a new topic. So we have already covered conduction and we covered convection. Conduction and convection were the two big topics. Conduction, multiple type conductions. We covered steady state conduction, one dimensional, two dimensional, then transient conduction, and then we studied in convection the external flows, internal flows, free convection, boiling, condensation, and then the heat exchangers, which was an application of conduction and convection as a whole. So we have completed till chapter number 11, and now we are going to start from chapter number 12, 13. There are two chapters which are related to the radiation. There are just two chapters here for radiation, but these chapters are comparatively not very easy to study, because you have a lot of terminologies in it which relate to this radiation thing, and you never have been familiar with those terminologies, and so it's kind of a difficult. But anyways, we're going to keep it simple and we're going to study the basics. We're going to remain on the surface. We're not going to go into a lot of depth. Anyways, the depth is there in your textbook, and if you want to go, you're obviously most welcome to go through it. So chapter number 12, that's about the radiation processes and properties. So right now in chapter number 12, you're not going to study the heat transfer. That's not the heat transfer that we are going to study. So we're going to study the radiation processes and the properties of radiation. How does the radiation behave, irrespective of the heat transfer? So we are not really concerned right now about the heat transfer. In fact, in this chapter, you're not going to study the heat transfer at all. Okay, so we are going to just study the radiation processes and the properties. Okay. So we're going to start with the fundamental concepts. We're going to talk about the radiation heat fluxes, then the black body radiation, emission from real surfaces, absorption, reflection, transmission by real surfaces. We're going to study the Kirchhoff's law. You studied Kirchhoff's law, right? But I was in the circuit. That's a different Kirchhoff's law. Kirchhoff did not stop there at circuits. Okay. Then we're going to study the gray surface results only. And there are some topics which we will not cover, but you are most welcome if you want to cover it from the textbook. So we are concerned with thermal radiations. Okay. So attention is focused on thermal radiation whose origins are associated with emission from matter at an absolute temperature. So whenever we have an absolute temperature, you know what is absolute temperature? Absolute temperature is Kelvin. Okay, so whenever we have any matter that has an absolute temperature will emit radiation. Okay, so even an object at minus 272 degrees centigrade will emit radiation, and an object at 1000 degrees centigrade will emit radiation. Okay. Emission is basically due to oscillations and transitions of many electrons that comprise matter. So obviously the radiations are because of the internal oscillations, internal vibration of the molecules that comprise the matter. So if there is any matter, it will have a certain absolute temperature, and if it has a certain absolute temperature, it would definitely emit radiations. So emission corresponds to heat transfer from matter and hence to a reduction in thermal energy stored by the matter. So when So the thing is that if there is a body and it is emitting radiation, so that means it is emitting energy. Emitting energy means energy is going out of the body. So actually the energy content of the body should decrease because some of the energy is going out. But at the same time, the body is also accepting energy. So the two phenomena are occurring at the same time. And if the body is at the same temperature and if the energy content of the body is not decreasing, that means the amount of energy which is emitted by the body is exactly same as the amount of energy being absorbed by the body. Okay? So a constant temperature does not mean that the body is not emitting energy. It is still emitting energy. But a constant temperature means that the amount of emission is equal to the amount of absorption at the same time. So temperature decrease mean amount of emission is more than the amount of absorption. Temperature decrease mean amount of emission is more than the amount of absorption, and temperature increase mean amount of absorption is more than the amount of emission. So it's like that. So move ahead. Now emission is basically if we have a semi-transparent material, so like you can see the jelly, something that you can see inside the body. So if we have a semi-transparent material, then the emission is basically a volumetric phenomena. So the whole body is emitting from the top at the surface as well as from the things which are inside. However, if we have an opaque object, okay, opaque object is an object where you can see the surface, you cannot see inside. Okay, so if I am standing here in front of the wall, I can see the wall surface only. Inside concrete, whatever we have, I cannot see that. That's an opaque object. So for an opaque object, it is basically a surface phenomena. So basically the energy is emitted from the surface only. Okay. So for an opaque solid or liquid, emissions originates from atoms and molecules within 1 micrometer of the surface. So just within the 1 micrometer thickness, emissions of the radiation is there. Now what is the nature of the radiation? Radiation has the dual nature. In some cases, the physical manifestation of radiation may be explained by viewing it as particles, as known as photons or quanta. So sometimes radiation behaves as particles. In other cases, radiation behaves as electromagnetic waves. Then they made up a third theory which says that it is the particles which are moving in the as waves. So that try to satisfy both the theories, because radiations satisfy as particles as well as waves, electromagnetic waves at the same time. Okay. So anyways, when we consider it as radiations as in the form of electromagnetic waves, so that means waves are like this, so there must be some wavelength. Okay. So so then it is characterized by the wavelength and frequency. Wavelength is lambda, frequency is mu. Okay. So frequency is number of waves per second, and wavelength is what's the actual dimension, what's the actual length of the wave. Anyways, so let's discuss the electromagnetic spectrum. So the electromagnetic spectrum, or the radiation emitted, the radiations, they could be seen as of different wavelengths. Okay. Now this is basically a log chart: 10 to the power minus 5, 10 to the power minus 4, 10 to the power minus 3, minus 2, minus 1, 1, 10, 100, 1000, 10,000. Okay. So if the wavelength is less than 10 to the power minus 4, beyond that we have the gamma rays. If it is between 10 to the power 4 to 10 to the power minus 4 to 10 to the power minus 2, then these are the X-rays. But the X-rays and gamma rays do not emit thermal radiation. They do not emit energy. Energy is not emitted by them. Okay. Then we have between 10 to the power minus 2 to 10 to the power minus 1, or exactly if we talk about to 0.4, we have the ultraviolet region. Then we have the visible spectrum. It's 0.4 to 0.7 micrometer. So the solar energy which you can actually see, for which your eyes are sensitive to, okay, is basically lying between the wavelength of 0.4 to 0.7 into 10 to the power minus 6. Okay, so that's the 0.4 to 0.6 microns. That's the visible spectrum. So we have the violet, blue, green, yellow, red, all colors. They are all within this spectrum. Okay. Then if we move further from 0.7 to 10 to the power 2, then this is the infrared region. And beyond 10 to the power 2, we have the microwaves. So basically our thermal radiation, or when we talk about the radiation heat transfer, so those radiations which carry energy with them, ranges in between 10 to the power minus 1 to 100. So 0.1 to 100. That's the range. So the wavelengths which are between 0.1 to 100 microns, that only emit thermal radiation. Okay, that only emits radiations which carry energy. The others don't carry energy. Okay, and within this spectrum, within this band, only 0.4 to 0.7 is visible. 0.4 to 0.7 is visible. The other is not visible. If it is, let's say, if there are ultraviolet radiations, when we have UV radiations, they are emitting energy, but you cannot see those radiations. Or if we have infrared region, they are emitting radiations, but still you cannot see them. Okay. So anyways, thermal radiation is confined to infrared, visible, ultraviolet regions of the spectrum. When we say spectrum, it means variation with wavelength. Spectrum means with variation of wavelength. Okay. So anyways, this graph is very important. This graph is very important to study. Now let's talk about the radiation heat fluxes. There are certain terminologies that you should know when we are dealing with the radiation heat fluxes. Okay. First of all, emissive power. Emissive power is E. So if you have any body, the body will radiate energy, and the amount of energy radiated by the body is its emissive power, depends upon its emissive power. How much is the emissive power of that body? Okay, so emissive power is capital E, rate at which radiation is emitted from a surface per unit area. As simple as that. Rate at which the energy is emitted from the body per unit surface area. Okay, then we have irradiation. You have radiation. If you put IR before radiation, that becomes irradiation. Irradiation means incoming radiation. So I have a surface, whatever the radiation is falling on the surface, that is irradiation. Incoming radiation. It does not matter from where this energy is coming from, but if it is coming and falling on the surface, then that's the irradiation. Okay?
What's the name of the outcome?
We'll talk about it. That's the emissive emission. If the radiation which is getting out of this body, okay, they could be of several types. Maybe that is kind of a radiation which is being emitted from the surface of the body.
Or from the volume.
okay, or from the volume. Let's say we are not talking about the semi-transparent, we're talking about the opaque bodies, then from the surface of the body, okay, then that is the emission. But there is another possibility that when the radiation, when the irradiation coming, when the incoming radiation falls on the surface, there is a possibility that part of that radiation is also reflected. So the reflection also seems like going out of the surface, right? So that is the reflection, that is not emission, okay? And the combination of the amount of energy reflected plus the amount of energy emitted is known as radiosity. So anyways, your question, all the amount of energy which is falling on the body, we call it irradiation. And all the amount of energy which is going out of the body is radiosity. Radiosity composed of two terms. Reflection and emission. Is okay? So, if you look here, let's say this is our body. Let's say this is our body. So we have irradiation. So total incoming radiation. Okay? So we represent it by G. G means irradiation. Okay? Now there is a possibility that a part of G, a fraction of G, is reflected from the surface. Okay? So that is known as reflection. Okay? There is possibility that part of that radiation is absorbed in the surface, absorbed in the body. That is known as absorption. Then there is another possibility that part of the radiation is transmitted. So no, from for example, it's a glass. So if it is a glass or semi-transparent body, then there is possibility that part of the radiation is going within the body and going out of the body. So that it passes through the body and emits from the other end. Okay? So that's known as transmission. It is transmitted through the body. Okay? So anyways, the total amount of energy, the irradiation, the total amount of incoming energy will be composed of three components. Okay? Reflection, absorption, and transmission. If it is an opaque body, if it is a body from which you cannot see through, then the transmission will be zero. So the total amount of irradiation will be absorption plus reflection. If it is a mirror, so mirror is an opaque body and it reflects everything. So in that case, absorption is almost also zero. But yes, sometimes there is also little absorption, because if you emit a lot of, if you have a lot of radiation over a mirror, the mirror might get a little hot. Hot means it absorbed something. But that fraction is too small, and most part is reflected.
So mirrors even they reflect heat?
Radiation. So radiations carry heat.
Like laser.
Hmm?
Like laser, that's all.
Yeah, any radiation. Radiation coming from these lights, they also carry heat. Okay. So anyways, for the case of opaque medium, transmissivity will be zero. Okay, so there is nothing as transmitted out. Then we have the radiosity. Radiosity, as Hamdi asked, radiosity is the total amount of energy going out of the surface of the body. That could be because of two reasons: emission and reflection. So combination of emission and reflection is radiosity. Okay, rate at which the radiation leaves a surface per unit area. That's radiosity. So it is represented by J, and J is equals to E, which is emission plus reflection. Okay. Is it clear, the terminologies and everything so far? Okay. Okay, now we have two terminologies. We call it spectral or diffuse. Okay, whenever we have something spectral, that means we are concerned about a specific wavelength. Okay, so specific wavelength, if we are concerned about the specific wavelength, that's a spectral. If it is for all, then it is total. So it's spectral and total. Okay, then we have another thing which is known as diffuse. Diffuse means equal in same direction, equal in all directions. Okay, so for example, I have a surface and a radiation is falling on the surface. If the surface is diffuse, then, and let's say it is opaque, and let's say all of the radiation is reflected. So, but if the surface is diffuse, then the reflection will be same in all direction. So diffuse means same in all direction. Okay. Let's say if I have a body and it is emitting radiation, but if the body is diffuse emitter, so diffuse emitter means it is emitting radiation same in all direction. Is it clear? Do you understand the word diffuse mean? Okay, when we have a mirror is not a diffuse reflector, because in case of a mirror, the reflection falls on the surface, but then angle of reflectivity, angle of refraction is the same as angle of incidence. Okay, so in that case, the radiation which fall on the surface is reflected at a specific angle, not in all directions, not same in all direction. Okay, so a mirror is not a diffuse reflector, but all these walls and surfaces, they are diffuse reflectors. Okay, so the radiation, all the light that falls on the surface, when they spread in all directions evenly, in equal amount in all directions. But the mirror is not diffuse.
Specifically. What is specifically?
For yes. So anyway, so here the important point was to understand the concept of diffuse. What does diffuse means? So a diffuse emitter means a surface which is emitting radiation but equal amount of radiation in all direction. That's a diffuse emitter. A diffuse reflector means it is reflecting radiation but equal amount in all direction. Okay. Now, as I told you, we have two terminologies here, spectral and total. When we say that something is spectral, that means something, its variation with wavelength we are counting. And when we say it's total, that means its variation with wavelength we are not taking consideration, we are taking the whole thing. Okay? So spectral irradiation. So irradiation is basically measured in watt per meter square, but when we talk about the spectral irradiation, that means for a specific wavelength. Okay? And when we have the total irradiation, so total irradiation means spectral irradiation integrated for the whole spectrum. Spectral radiation integrated for the whole spectrum for the entire wavelengths. The total amount of radiation, total amount of energy. Okay? So G, when we put a subscript lambda, so that means it is a spectral. When we do not put a subscript lambda, that means it is total. Okay? Spectral means we are now concerned with a specific wavelength. Not a spectral, total means that all the wavelength together.
That's why he took that together.
Yes. Okay. So you see here you have the irradiation, let's say part of it reflected, and then you have the emission plus G reflected, that total makes it radiosity. Okay, and G reflection would always depends upon the reflectivity. Okay, so G reflection would depend upon the reflectivity, where G is the total irradiation. So total amount of irradiation, a fraction of it, let's say 20% of it is reflected. Okay, so we have the reflectivity in terms of the percentage of the total irradiation. Now let's talk about the black body radiation. Now black body is a body which is defined, which has a specific definition, and there are 3 points based on which a black body is defined. You should remember the 3 points. If I ask you what is a black body, you should define the black body by these 3 points. So a black body is an ideal emitter. If you have any body which is emitting maximum amount of energy, that's one of the definition of a black body. Then the second thing about black body is an ideal absorber. So all the radiations that come towards the black body, it absorbs it.
And it's emitting at the same time.
And it's emitting at the same time. So the total content does remain same. Okay.
It's constant.
Yeah, obviously. So it's an ideal absorber. It absorbs all the radiation which falls on it. Okay. And the third point of the definition is that a black body is a diffuse emitter. When the emissions are made by the black body, that emission is not in a single direction. That emission is in all the directions in equal amount. That's known as diffuse emission. Okay? So that's the definition of a black body. What is a black body? A black body is an ideal emitter. It is an ideal absorber, and it is a diffuse emitter. When it emits radiation in all directions in equal amount. Is it clear? That is the definition of a black body.
Is it the same as a black hole in space?
Yes. In reality, in the world, we do not have black body anywhere, because there is no body which is an ideal emitter and an ideal absorber at the same time as a diffuse emitter. Okay, so ideal absorber means whatever radiation comes, it absorbs everything. Okay, so how do we see things? Light comes and falls on a body, is reflected back, and when goes into our eyes, we see the object. If all the light comes and falls on a body and is absorbed by the body, nothing comes out, then how will we be able to see it? We won't be able to see it. Okay, so that's the thing. In the world, we do not have black body. Black body is an idealized body. Okay, it's the reason why we call the black hole as black hole in space, because it takes all the energy in it and we don't know what's inside. Okay, anyways, so we can actually, there is no black body, but we can idealize or make a body setup which is very close to the black body. Okay, so suppose this isothermal cavity, also known as holoron. Okay, this isothermal cavity holoron is an idealization or some approximation of a black body. Okay, so if you take a holoron such that it is an enclosed surface, okay, and there is only one small opening, so what will happen? Any light or energy which will enter into that opening will be reflected and eventually will be absorbed by the body at all. Okay, so that's the perfect absorption. Okay, So that is kind of an approximation of a black body. It absorbs everything. Okay? So that's an ideal absorber. Okay. So in the isothermal cavity, after multiple reflections, virtually all radiation entering the cavity will be absorbed. So it's kind of making of a black hole. Obviously, it's not the perfect one, but an idealization, an example of it. So it's known as isothermal cavity. Okay, so now let's talk about the spectral Planck distribution of black body radiation. Okay. Now the thing is that the amount of energy, okay, the amount of energy emitted or the emissive power of any radiation, okay, varies with the wavelength. Okay. As well as it varies with the temperature from at which it is being emitted out. Okay. So if we draw this spectrum, if we draw the spectrum for all the wavelengths, okay, with the amount of energy emitted for different temperatures, the spectrum would somehow look like that. Okay. So for 50 Kelvin. So for one thing is very clear, that for each temperature you reach an emissive power of maximum at a certain wavelength and then it reduces. Okay. So if this is the emissive power, okay, so the curve would be like this, okay, with the variation of wavelength. Okay, so for each temperature, the emissive power will initially increase, reach to a maximum, and then drop with the increase in the wavelength. Okay, so there will be a peak amount of emissive power. Okay. Now, one thing, if we realize, or if we check in it, that let's say this is temperature T1, this is T2, this is T3. As we increase the temperature, the peak increases. So that makes sense. The body which is at high temperature would emit larger radiation. Okay. However, as we decrease the temperature, the peak decreases and it shifts towards larger wavelength. Okay. So if we draw the locus of the points for all the peaks, it will be kind of a straight line. It will be kind of a straight line. Okay. And that has a negative inclination, a negative slope. Okay, and so for lambda max t, so lambda max t will be a constant. You know, for a negative slope straight line, we have an equation like that. Okay. So lambda max t will be a constant, and that constant will be 2898 micrometer Kelvin. And that is the Wien's displacement law. This law is known as the Wien's displacement law. So for any emitted radiation, the lambda max multiplied by temperature is basically a constant value. And this is basically the slope, which is 2898 micrometer Kelvin. How do we determine it? Basically, we integrate, we evaluate this terminology. Okay, so we have the total energy emission as a function of lambda and temperature is given by this terminology, where the constants are known as the first radiation constant, second radiation constant. Then in your book you have the complete derivation. At the end of the derivation you come up with this result that lambda max T is equals to a constant which is 2898 micrometer Kelvin. Okay. Anyways, we are not going to go into that derivation. So the important point for you here is that lambda max T is a constant, which is known as Wien's displacement constant. Now the thing is that if we want to know the total amount of energy emitted at a specific temperature, so let's say I have a specific temperature, so the amount of emissive power from it is like this. Okay, so the total amount of energy emitted for all the wavelengths will be area under the curve. Will be area under this curve. Okay, and once we do that integration, so we have this E as a function of lambda and T, but this is a very difficult integration because we have lambda here on the denominator side with power multiplied inside the exponent as well. So it's like one-page integration. It is there in the book. However, once we do it, we're going to end up with this thing that the total emissive power for any specific temperature will be equal to sigma T into power 4. This is the Stephen Boltzmann constant, which we studied in chapter number 1.
Yes.
Okay. So that's the Stephen Boltzmann law. Anyways, it comes out as a result of integration of this equation. It comes out as a result of integration of this equation from 0 to infinite, employing the radiation constants. So we got this, that the total amount of energy emitted by all wavelengths at any specific temperature will be equal to sigma into T to the power 4, where sigma is the Stephen Boltzmann constant and its value is 5.67 × 10⁻⁸ watt per meter squared Kelvin power 4. So that's basically known as the Stephen Boltzmann law. Now let's talk about the band emission. Now this was the emissive power of the entire spectrum. But if we want to know the emissive power for a specific wavelength, so let's say that we want to know what is the specific power from the wavelength from 0 to lambda 1 till this point. So in that case, we need area under the curve till this point only. Okay. So it will be what? Now the thing is that means now we have to solve this integral again, but instead of 0 to infinity, we have to solve it 0 to lambda. And let's say 0 to lambda 1, or let's say 0 to lambda. Okay. So E lambda d lambda. Okay. Now the thing is that this integration is already solved, and it is present in the form of fraction in this table. Okay. So what we do is that they have found out a fraction for any specific frequency range to the total amount of energy emitted by all frequencies. Okay. So this fraction f is basically what? It's integral 0 to lambda E lambda d lambda divided by integral 0 to infinity E lambda d lambda. So they have already evaluated this fraction, and it is present in table 12.2. Okay. So if we want to know from 0 to lambda 1, we just need to know what is the fraction and multiply it by this thing, which is basically sigma into T to the power 4. Okay. So this fraction is evaluated for lambda t. So if the lambda t value is this corresponding to this, these are the fractions. Okay. So when the lambda t value is small, the fraction is small. When the lambda t value is larger, the fraction is larger. When the lambda t value will be infinity, the fraction will be totally 1. Okay. So when this lambda approaches infinite, so the fraction will become 1. Yeah. So when this lambda approaches infinite, the fraction will become 1. When this lambda is 0, the fraction is 0.
0, yes.
Yeah. So that's it. That's how it is. So this is a very important table that you will be using in your analysis. Again, to remind you, this chapter we are discussing just the radiation processes and properties, not the heat transfer associated with it. We are going to move towards the heat transfer associated in chapter number 13, not chapter number 12. In chapter number 12, we are discussing something very different, just the radiation processes and the radiation properties. These are the radiation properties. How does the radiation behave? Okay, that's it.
The first column here is for
The first column here is for lambda t. It's a combination of lambda and T. T is the temperature in Kelvin of a body emitting radiation. Okay, and the second column is the fraction, which is this fraction from 0 to lambda. Okay.
the other two columns.
Other two columns we are not right now concerned here. Okay, but they are about the intensity. But that's a little going into deep. Okay, so we are not really much concerned here about it. So now let's talk about it. What do you think will be the temperature of the wall here? Around 20 degrees? As the room temperature, but if you touch the wall, it will be slightly cooler. Okay, so let's say if it is 23 degree or 22 degree, so what will be the value in Kelvin?
296 Kelvin.
296 Kelvin, right? So if it is 296 Kelvin, so what will be lambda t? So lambda t will be sorry. So what will be the emissive power here? Now there is one more thing here, that when we plot this, so when we plot the maximums, so the lambda max t is a constant, and that is known as the Wien's displacement constant, and it has a specific value which is 2898. Okay. So now let's consider that the amount of radiations emitted by this wall lies in what wavelength. Okay. So if we see here, lambda max t is equals to 2898. Okay. And if we look at this curve, so 2898 has a fraction value of around 0.25. So f0 to lambda is 0.25 for this fraction. Okay. Now when the wall temperature is 298 or let's say 296 Kelvin, so what will be lambda max? Lambda max will be 2898 divided by 296. Can you do it? 2898 divided by 296. 9.79. That's the micrometer. So if you see here, in the overall spectrum, 9.79. 9.79 means this wall is emitting radiation, but that radiation is in the infrared region. That's why we are not able to see the radiations which are being emitted by the wall. Now, the sun temperature is approximated to be around 5,800. So the temperature of the sun
Celsius.
is 5,800 Kelvin. Okay. So in that case, lambda max T will be 2898. This is a constant, 2898. Okay. So what will be lambda max here? So 2898 divided by 5800 for the sun, the amount of radiations emitted by the sun. So what will be lambda max here? 5800. 0.0 no.
No.
2898 divided by 5800 cannot be
0.499.
0.499. Or you said 0.9
Yeah.
something. Okay. So 0.49, if you see here 0.49, it exactly lies in between our visible spectrum. 0.4 to 0.7. It's around 0.5, 0.49. That is the reason the radiations emitted by the sun are visible to us. If you have an iron and you heat the iron, so its temperature will keep on rising. A time will reach when the temperature of the iron will become so high that it will become red hot.
Yes.
So now we are able to see the radiation emitted by the iron when it becomes red hot.
Yes.
Right? Okay. So if we want to know that what would be the temperature needed so that we will be able to see the radiations emitted, okay? If we want to know what is the temperature needed that we will be able to see the radiation, so we have 0.4 and 0.7. That's our range for which our eyes are sensitive, okay? So let's say if our lambda max is 0.7, so we have lambda max T is equals to 2898. If we say that our lambda max is 0.7, find out the temperature. 4,000. Yeah, 4010. So that means when the temperature of any body will reach to that point, I will be able to view I will be able to see the radiation emitted from that body. Okay, that is if it is 0.4, then
For 0.7 you will be able to see the red light.
yes, exactly.
For 0.4 will be the light.
So 2898 divided by 0.4.
It's 7,245.
Yes. So that's the range. So if the temperature is between these ranges for a body, then we will be able to start viewing the radiations emitted from it.
What's
Okay.
next, Doctor?
Hmm?
What's next?
What's next means what?
Beyond this temperature.
There is nothing beyond this temperature.
Really?
Okay. Yes. Okay, so let's have a numerical associated with it. It's actually a bit boring chapter in the sense that we are not actually dealing with the heat and mass transfer. We are, huh?
The nice object that we have here.
Sorry?
From the beginning, it's the beautiful chapter.
Really?
We don't like you.
Okay. So let's have a numerical. Consider a large isothermal enclosure that is maintained at a uniform temperature of 2000 Kelvin. So we have a large isothermal enclosure. Enclosure means any enclosed body, any enclosed cavity. And the surface temperature of it is 2000 Kelvin. Calculate the emissive power of the radiation that emerges from a small aperture on the enclosure area. So first of all, we have so we have a body which has a temperature of 2000 Kelvin. Okay, so first of all, what do we need to find out? We need to find out the emissive power of the radiation that emerges from the small aperture. Okay, since we have an enclosure, so this enclosure, as we discussed, behaves as a black body, because the amount of energy emitted by it will be exactly the total amount of energy emitted by this enclosure. Okay, so if it behaves as a black body, then what we need to find? We need to calculate the emissive power. So for a black body, the emissive power, total emissive energy, is basically sigma into T power 4. So emissivity of the black body is 1. So emissive power is sigma into T power 4. Sigma is 5.67 times power minus 8. T is 2000 Kelvin. So we know the temperature, we know the value of sigma, we will know what is the emissive power. Is it clear? Calculate the emissive power of the radiation that emerges from a small aperture of the enclosure surface. What is the wavelength below which 10% of the emission is concentrated? Now we know that when the emission is there, when the radiations are emitted for different wavelengths, and the amount of energy radiated is distributed among those wavelengths. Okay, so the wavelength spectrum would again be like this. Okay, but now what we need to find out is that this is the total energy. This is the total energy, and that is equal to this thing. Okay, now we need to find out that what is the wavelength below which 10% of the emission is concentrated. So this is the total emission, but what is the wavelength below which 10% of the wavelength is there? So 10% of the energy is concentrated below which wavelength? Okay, and what is the wavelength above which 10% of the emission is concentrated? So what is the wavelength above which 10% is concentrated? That means below which is 90%. Okay, so we need to find out this wavelength lambda 1 and this wavelength lambda 2, above which is 10%. Okay, now we can determine it using the table 12.2, which was related with the fraction of emissions for different wavelength. Okay, so we have lambda t. Okay, we need to find lambda t. So if temperature is fixed 2000 Kelvin, okay, so for the first case lambda 1, when we need to find out, so now we know that the fraction here should be 10%. So that's the fractions. So that is 10%. Okay. So now we need to find out for f0 to lambda if it is 0.1, which is 10%. If it is 0.1, what is the value of lambda t?
0.1 over the temperature.
So if we go into the table, so f0 to lambda, the fraction when it becomes 10%, 0, 0, 0, 2, 1, 3, 6, here it becomes 10%. So 0.110 would be between 0.06728 and 0.100888. Okay, so you do the interpolation and find out exactly what is the temperature, what is lambda t. Okay, so you know that you want to know the wavelength for this fraction, 10%. So corresponding to the fraction, you find out what is lambda t. Okay, so the lambda t will be between 2000 and 2200. Okay, so once we do the interpolation, in this case the lambda t comes out to be 2195. Okay, so lambda T comes out to be 2195. Now we know the temperature, so we can find out what is this lambda 1. Is it clear? So once we substitute the value of temperature here, so the lambda 1 comes out to be 1.1 micrometer. That means for the complete spectrum, from the wavelength from 0 to 1.1 micrometer, 10% of the energy is there. 10% of the energy is associated in that portion. Okay. The second part of the problem, what is the wavelength above which 10% of the emission is concentrated? So we need to find the second wavelength above which 10% of the energy is there. Okay. So now we need to take the fraction 0 to lambda 2, because all these fractions are 0 to lambda. Okay. But we need lambda 2, right?
It will be 90, not 10%.
Yes. So it will be 90%. Okay, so that fraction now from 0 to lambda 2, it should be 0.9. Okay, so if it is 0.9, so now lambda 2t is equals to, for 0.9, let's see. Okay, the table here is not complete here because it is ending here at 0.48. Then we have the second page, so it is there in your book. Okay. Table is complete in your book. So it will come out to be lambda 2t will be 9382. Obviously you need to do interpolation. Okay, 9382. So now you know the temperature, so we can find out what is lambda 2. So lambda 2 will be 4.69 micrometer. So that means from 0 to 1.1 micrometer, 10% of the energy is there, and from 4.69 micrometer to infinite, the remaining, the last 10% is there in that region. Is it clear?
Yes.
Okay, so now let's talk about surface emissivity. Now surface emissivity is a property, look, every surface is emitting radiation. Every surface is emitting radiation, because any surface which has any absolute temperature will emit radiation. But what we assume is that the maximum amount of radiation emitted by a surface is by the black body. So that's an idealized body. An idealized body, black body, emits maximum amount of radiation. So whenever we would like to see how good a body is emitting radiation, we compare it with the black body. Okay, how good a body is emitting radiation, we compare it with the black body. So a body temperature is 100 degrees centigrade. How well it is emitting radiation? So how do we compare? If a black body is at 100 degree, how much radiation will that emit compared to this body? If a body is at 1000 degrees centigrade and it is emitting radiation, how to compare that? How good is it, or how much emission is there? So we compare it with the black body. If there was a black body which was emitting at 1000 degrees centigrade, then how much radiation would that be compared to how much emitted by this body? Is it clear? So we always, we now make black body as our reference for analysis. Okay, so we define the term emissivity. We define the term emissivity epsilon as the emission from the body over the emission of the black body. So emissivity is what defined as what? Emission of the real body divided by the emission from the black body at that temperature. Obviously it depends upon temperature. Okay, so emission from the black body is how much?
1.
Lambda T power 4. sigma T power 4. Okay, that's the emission from a black body, total emission. Okay, and emission by the actual body, it depends upon its emissivity. Okay, and then this is the emissivity. Okay, so we define emissivity from this relation. Emissivity is equals to E upon EB. E is the emission from a body divided by EB is the emission from the black body. Okay, or we further write it as emission from this body is equals to integral 0 to infinite emissivity, which is a function of lambda and T, into emissivity of the black body, which is function of lambda and T, d lambda. Okay. So this is how we write it as the total emissivity of a body. This is how we write the total emissivity of the body. Is it clear?
EB is sigma T to the power 4.
Yes.
But in E, only E.
The only E is, so basically only E will be what? Only E is epsilon into EB, right? Only E is epsilon into EB, right?
Yes.
So E I have written here as epsilon into EB, but there is a possibility that epsilon varies with lambda and time. So then we have to write E as a function of lambda and time as well. Okay. So now I substitute this thing here, but with the integral format from 0 to infinity. It's clear?
Yes.
This is a very complicated chapter in the sense there are many new terminologies here and many things. So just stay with me or focus with me only on the things which I emphasize, which I'm discussing in the class. The things which I skip, you can also skip. Okay. Let's have a problem. A diffuse surface at 1600 Kelvin has the spectral hemispherical emissivity. These emissivities, if I have any surface and it is emitting radiations, so the emission is called as hemispherical emission because it's like a half sphere. The emission is there over the half sphere. So if I have the surface, let's say this is the surface, okay, and it is emitting radiation, so it's emitting radiation here, 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 here. That's the half sphere throughout which emission will be there. Okay, so that's why it is known as hemispherical emission. Emission in the half sphere. Okay, so a diffuse surface at 1600 Kelvin has the spectral hemispherical emissivity shown. So that's the spectral hemispherical emissivity. So from 0 to 2 micrometer, from 0 to 2 micron, emissivity is 0.4. Then from 2 to 5 micron, emissivity is 0.8. Then from 5 micron to infinite, emissivity is 0. Okay, we need to find out what is the total hemispherical emissivity and the total emissive power by this surface. Now the total hemispherical emissivity we will determine by this equation. Epsilon is equals to integral emissivity 0 to infinity as a function of lambda E as lambda d lambda upon EB. Right? So that was emissivity epsilon is equals to E by EB. Right? It was like this. Now this is 0 to infinite. Now here what we do is that we do the integration by parts.
So we take each part.
Yeah. So now let's subdivide this part 0 to 2, because we know that from 0 to 2 we have one specific emissivity. Okay, 0 to 2, and here epsilon 1. Okay, E lambda, D lambda. Okay, plus 2 to 5 epsilon 2 E lambda D lambda, plus 5 to infinity. Okay, and call it epsilon 3. Yeah, so it's epsilon 3 E lambda D lambda, and this is all divided by EB, right? So this is by EB, this is by EB, this is by EB. Is it clear? So we had this thing 0 to infinite. We need to find the total emissivity of the body, of the surface. Okay, but the emissivity of the surface depends upon the wavelength. So from 0 to 2 wavelength emissivity is 0.4. 2 to 5 emissivity is 0.8, and then 5 to infinity emissivity is 0, right? So now for this integral, emissivity 1 is constant, emissivity 2 is also constant, emissivity 3 is also constant. So I can take these emissivities out, right? So let's take this out. So it becomes epsilon 1 here, it becomes epsilon 2 here, and it becomes epsilon 3 here.
The third part, can we assume it as a 0? Because it's
Yes.
0.4, 0.8.
Okay. Now in the third part, what is the emissivity here? 0.
You cancel that term.
So we can cancel this term. Okay. Now this is what? Epsilon 1 multiplied by this term. Now this term is basically what? This is F fraction 0 to 0 to lambda for 2 microns. Okay. Or I will say here 0 to 2, because this lambda is basically 2 micron here. Okay. Plus epsilon 2, this is basically what? F from 2 to 5. Is clear? So I have epsilon 1 F 0 to 2, epsilon 2 multiplied by F 2 to 5, and this term will be 0. We know what is the emissivity in the first portion. We know what is the emissivity in the second portion. Emissivity in the first portion is 0.4, emissivity in the second portion is 0.8. Okay. Now we need to know what is F0 to 2. Okay. F0 to 2, for finding that, we will go into the table. Okay. Now, in order to find F0 to 2, if you see in the table, we need to know what is lambda t. Okay? We need to know what is lambda t. You see in the table, for finding F0 to 2, we should know what is lambda t. Okay? Now, for our case, the temperature is known. It was 1600 Kelvin, the diffuse surface. Okay? So we can find out what is lambda 1t. So lambda is 0 to 2, so it's basically 2. All values are 0 to that. Okay? So it's 2. So we have 2 multiplied by 1600. So that is 3200. Right? So for 3200, if we see that value of F0 0 to lambda will be 0.318. So we will know what is F0 to 2.
We could have in between values.
Is this step clear or not? Okay. So we needed to know what is this fraction f0 to 2. Okay. Now we need to know f2 to 5. Now if you see here in the table, everything is 0 to lambda. Everything is 0 to lambda. We need to know 2 to 5.
0 to 5 minus 0.
0 to 5 minus 0 to 2. Okay. So if we have a curve like this, and we need to know emission only this band, where this is 2, this is 5, 2 to 5. So what we do is that we find 0 to 5 minus 0 to 2, so that will give us 2 to 5. So now this thing will be f2 to 5 will be f0 to 5 minus f0 to 2. f0 to 2 we already know. Now we need to know what is f0 to 5.
5,000.
Okay, so for f0 to 5 we should know what is lambda 2t. Okay, so t is known, lambda 2 is 5, so 5 into 1600, that will be 8,000, right? So for 8,000, now here this table is not completed. In the second part we have lambda t. Okay, so for 8,000, it comes out to be 0.856. Okay, so now we know what is f0 to 5, 0.856.
We subtract them.
So we subtract them, multiply by epsilon 2 plus f0 to 2 multiply by epsilon 1. We will get the total emissivity of that surface. Okay, so the total emissivity of the surface comes out to be 0.558. Total emissivity of the surface comes out to be 0.558. Now we need to know what is the emissive power. So by the original equation, epsilon is equals to E upon EB. So now we know what is epsilon. We know what is EB. EB is sigma T power 4. Multiply them together, we will find out what is the actual emissive power of this surface. So the actual emissive power of this surface comes out to be 207 kilowatt per meter square.